moderator for today's webinar, Deoiling Solutions for oil and gas companies. Oil and gas producers and refiners are seeking water deoiling solutions for produced water, for raw water, wastewater applications, and groundwater remediation to ensure better environmental stewardship and compliance. This webinar is going to discuss primary, secondary, and tertiary oil water separation, and we'll review a few live applications. This webinar will be 30 minutes in length, and then we'll do a 15-minute question and answer session. Before we start the presentation, here are some housekeeping notes. You should be hearing me speak right now. There are two options for audio. You can listen either via your computer or you can call in with the call-in number in your confirmation email. So if you're having issues with your computer and the audio, just go to that email and call in. Also on the right hand of your screen, there's a questions panel. So feel free to enter your questions there. Everyone is muted, so we won't hear you speak, but you can type in questions in that panel. After the webinar, hold on a second. After the webinar, you'll be directed to take a 3-question survey. So please take it and give us feedback on today's presentation. You can also give us ideas for future webinars on water, wastewater, and other filtration and separation topics. So your feedback does matter. The next webinar for oil and gas companies will focus on high recovery membrane technologies. So go ahead and sign up now at veoliawatertech.com/events. That will be on Thursday, November 7th, just a few weeks away. It will focus on a few technologies designed for high fouling and scaling applications, such as the treatment of produced water, cooling tower blowdown, and refinery wastewater with a membrane treatment approach that achieves high water recovery and stringent water quality requirements. This webinar will also review an upstream and downstream oil and gas case study. So now let me introduce our presenter today. Dwayne Germanis is a Director of Business Development in oil and gas for Veolia Water Technologies. He has 30 years of water treatment experience in the oil and gas industry, and he lives in Houston, Texas. Thank you, Dwayne, for presenting today. The floor is yours.
Great, thank you, Dennis. I appreciate the intro, and welcome to all those in the Central Time Zone. Appreciate you spending your lunchtime with us. Hopefully, by the end of the presentation, you'll be able to learn something. I always like to do these webinars and hopefully teach you something new. We do these webinars fairly regularly, like we do lunch and learns. So this is one way we can reach out to the people that are interested in water treatment, like Dennis said, in the oil and gas space. And by the way, I'm in Houston, home of the Houston Astros, so go Stros for those baseball fans out there. So today we'll start off looking at technologies that fit into actually 3 categories. We'll start with primary, and then there's also equipment that fits into the secondary and tertiary mode. So each one of these will have equipment that will be able to treat the water at these different levels. A few things I'd like to say before we even start as well. When we talk about oil and water separation, today we'll be looking at removing free oil in these technologies. And when I say free, that means total oil and grease. You might have seen the acronym TOG, and that stands for total oil and grease. So I wanted to make that clear right up front. We're not talking about TPH, which is total petroleum hydrocarbon, and that includes hydrocarbons that are water soluble. So you might have heard some terms, WSOs, that stands for water soluble organics. All of the equipment we'll be talking about today does not treat organics. That's another whole webinar in itself. Key to point out, most of these technologies that we're going to be discussing can be used both offshore and onshore. We've even got a section on hydrocyclones that are mainly used offshore because of their small footprint and their sensitivity to motion, but very, very much so that you can use them onshore in multiple applications. So just wanted to point that out up front too, that for this topic, most of these technologies we'll be talking about onshore. Once again, offshore is another whole webinar in itself. So, but for this webinar, we'll be talking about onshore. Okay, next slide. So before we even talk about any of the technologies, I always like to start off with this slide. And as you'll see on the left, the separator type are going to be several topics we'll talk about. The API is the first one. That's a gravity-based separation system. And what I want to point out in this limitation of separation technology is the effect that oil droplet size has on any kind of oily water separation that you will get. So you'll notice in this chart, as you go down the list, we'll be able to separate smaller oil droplets down to the less than 1 micron range. For today's topic, we're going to be talking about line item 2, the CPI, the Corrugated Plate Interceptor, which is a little bit better than an API separator because we now have a coalescing part of the CPI, which is a plate pack. And you can see on the droplet removal range on the right there that just by adding some coalescence to a gravity-based separator, we can now, instead of getting 150 micron particles, now we can get 50. So it's a huge effect if we can grow those oil droplets. And as we go down the list, we'll be talking intensively on DAF, which stands for dissolved air flotation. IGF is induced gas flotation, and DGF is dissolved gas flotation. We'll look at a couple of those technologies in this presentation. Once again, now these types of technologies use flotation as the separation method. And now, once again, we can cut those micron size almost in half. And these are a range. Some technologies out there, whether it's ours or anybody on the market, can go a little bit below or a little bit above that, but this is a range. And this is an average of several different technologies, but it gives you an idea of what different separation method can do and boil down to getting those small oil droplets. The next one we'll look at is the liquid. The L/L stands for liquid hydrocyclone. And now we're going to use centrifugal force. And so instead of relying just on gravity, we're going to enhance gravity and use centrifugal force to spin the fluid and then get those smaller particles. Now we're down to the 15, 20 micron range. Once again, there's some hydrocyclone companies out there that can claim they get down to 10. All of these micron size oil particles in effect is getting about 90 to 95% separation efficiency. So we can still get some of the smaller ones. You just won't get as many of them from an efficiency standpoint. Moving down one more, you see a centrifuge, and that's a rotating piece of equipment. So once again, you're spinning it faster, and now you can get down to that 5 to 20 micron range. And then the last couple of them, coalescing filter, we'll actually look at a walnut shell filter for this one, where we use filtration and coalescence. We can get down to 2 micron. And then if you go into any kind of membrane technology, a UF, RO, nanofiltration, we can get down to less than 1 micron. And then one thing that's not on this slide is cartridge filters. You can buy cartridge filters to remove oil and water, but then you have to dispose of them. And there's all different sizes that go down to 0.01, 0.05 microns. So this gives you a good stage for what we're about to talk about. Next slide. So let's start in the primary. So corrugated or tilted plate interceptors. So you see that acronym sometime on bid documents or RFQs. CPI stands for Corrugated Plate Interceptor, and TPI is the tilted plate interceptor. We have both technologies within Veolia, They're a couple of different business units, but they basically do the same thing. Next slide. So whether it's a CPI or TPI, as we said in that one slide about what kind of separation method we are, we're coalescing oil droplets as they come in. So you'll see on the picture on the right a bunch of parallel plates. That's actually a plate pack that's tilted for a reason. Some people use 45 degrees, some people use other angles, but at about a 45-degree angle, the oily water enters the bottom, and as it goes up the plate packs, you're actually going to coalesce. You're going to grow those oil droplets. So in any type of deoiling technology, it's obviously easier to get those big oil droplets than it is a small one. So if there's any way we can coalesce or grow those oil droplets, it's just going to be that much easier to separate. As it goes through the coalescing plate pack, you'll see the oil and it goes up to the top. So oil is lighter than water. We've got a skimmer on the top. It skims off the oil, and the clean water then goes out another place where there's no oil left. The plate spacing allows particles to rise and settle faster. We can adjust the spacing between the plate packs. So depending on your application, if it needs to be a little closer or needs to be a little wider, we look at all the different design parameters that comes in to determining what that spacing might be. From a loading standpoint, most CPIs or TPIs can handle several thousand ppm coming in, and as well as solids. So effective bulk removal, 70 to 80, one might get 90% efficiency depending on the application. So it's that range of solids that we can get, and we can then. So if you have 1,000 ppm, we can usually get 100 ppm out of it. 90%, 85, 90%. One thing I forgot to mention, but it just triggered me here with Stokes' law. If you have been around separation for a while, I'm sure you might have heard that Stokes' law is the governing law that determines a lot of how oil and water can separate. So the equation has several parameters in it, and without describing the equation, it has to do with oil drop rise velocity, the density of the two phases that you're trying to separate, i.e. in this case, oil and water, and then the diameter of the oil droplet. So like back on the chart, when I talked about the different technologies, that is a parameter in the equation that is squared. So obviously, if it's a big number, if the diameter of the droplet's big, it makes it easier to separate. And then on the bottom of the equation, you have the viscosity of the water phase. One of the golden rules of thumb that I've seen, and I've actually looked it up in a book by John Walsh, that Stokes' law rule of thumb is described this way: a 100 micron drop will travel 10 centimeters in 1 minute. So if we were to try and calculate how much oil rises in a vessel, in a CPI, a float cell, whatever it may be, we can use that rule of thumb to determine what kind of separation efficiency you might get. One of the downsides of CPIs is plate fouling can happen. If the solids get stuck in there, you have to take the plate pack out and clean it and put it back in. It's not that big a deal, but it does. It's not one of the pros of it. It's one of the cons. But still, a very effective technology. Has been around for probably 35, 40 years, and still used today on many onshore applications. All right, next one. So let's look, we're still in the primary category. Let's look at liquid hydrocyclones. So one of my first jobs I had when I was getting into the water business, I was a service engineer, and this is about in the early 90s. And one of the things is my boss told me at the time, he says, if you want to learn how these things work, go look at it in the field. So I had a test unit, and you'll see that drawing on the screen there. Those are called liners. All the pieces, all the guts inside of a hydrocyclone have individual liners, and we'll talk about how this separation works. But I would take a single liner that had a control valve, a manual valve on both sides, and I would literally spin fluid in the field to test and see if a hydrocyclone was a good application for separating oil and water. So as I go through, I might reference a lot of jobs that I've been on because I was physically out in the field for many, many years before getting into business development. Next slide. So how do they work? So obviously, as we said in that one chart, we're using centrifugal force to separate the oil and water. So you'll see on the drawing the cutaway. So that's a vessel cut in half. All the individual liners inside that vessel. You can see the inlet chamber where the oily water comes in, and each one of those hydrocyclone liners has a tangential inlet. So pause with me for a minute, look up, and you'll see on that drawing on the top, that's an individual hydrocyclone liner. So that you can see where the oily water enters. It enters tangentially, and the fluid starts to spin. So there's nothing in there that's spinning. It's actually the fluid, the pressure of the water coming in. Each one of those liners has one of those tangential inlets, and you start to spin the fluid. As you go down through the tube, through the liner, you'll see the swirling action. The heavy phase will go to the outside, and the light phase is forced to the middle. And in a few slides down the way, I'll describe it a little more detail, but the oil goes out one way and the clean water goes out the other way. The pressure ratio is the pressure ratio of two different pressure drops. So if you think about looking back on the picture, the inlet to the reject is 1 delta P, and the inlet to the outlet is another delta P. That ratio needs to be greater than 1.3 to 1.5. We usually run about 1.7. But that's where a lot of the efficiency and how it works, it goes into play. Separation is proportional to that pressure drop as well. So the more pressure drop we can get, the better separation efficiency you can get. And within Veolia, we have what's called a streamliner design. And that design is the design of the hydrocyclone. We have several tangential inlets, multiple inlets to improve wear resistance. And we can retrofit into existing installations. Next slide. So what's the inlet typical? So like I said, I've been a service engineer running these things in the field. That is a typical 200 to 2000 ppm. Matter of fact, I was just given a training class the other day, and I've actually done percentage oil. So 1%, 2%. So 1% is 10,000 ppm, 2% is 20, and so on. So it can handle actually larger concentrations of oil. And as I get to the slide where we look at the liner, you can actually increase the diameter of the reject stream and handle more inlet concentration. But typically, this is what we would see, especially offshore. That's a typical concentration of oil that'll come out of a 2-phase or 3-phase separator or a free water knockout. Once it goes through the hydrocyclone, then you decide if you need secondary or tertiary treatment, depending on what the effluent is. Typical outlet, yeah, if you had 200 to 2000 come in, we could get down to that 25 to 100 ppm range. That next point is key. Oil must be free, so it doesn't do well on emulsified oil. So if you have emulsified oil, if there's a way to break that emulsion first, you're good to go. If not, you're not going to get that emulsified oil with a hydrocyclone. It just doesn't spin out. Next slide. So along with liquid, we've got two pictures here of liquid and solid liquid. So solid liquid hydrocyclones have been around a long time. Goes back to the mining days in the late 1800s when they were separating rocks from water. They'd use them in gold mines, lead mines, silver, whatever. So solid liquid cyclones came on the picture in the oil field in probably the late 60s, early 70s, maybe even a little earlier than that. But if any solids need to be removed, you could use a solid liquid cyclone or let them sit in the tank and let the solids just drop out. But same thing, you get the benefit of using centrifugal force to spin the fluid and have solids drop out. With that said, one of the things that's mandatory on a solid liquid cyclone is you have to be in the vertical position. And then you get not only centrifugal force, but gravity forcing it down. Back on the liquid, you can actually have them either in the vertical position or the horizontal. I've seen them tilted. You can have a 45-degree angle. The centrifugal force is great enough that it can be oriented in any position. But for the drawing programs, we just show them in a vertical position. So sometimes you might want to go liquid-liquid, then solid-liquid. Better pressure profile, oil sticking the solids may separate into the water phase, and abrasive solids in both systems. Or you'll go the other way. If you have a lot of solids, you want to get those out first, you can go through the solid liquid cyclone and then go into liquid liquid. And there's a pump on the bottom drawing that shows you might have to pump it to get it back up to pressure. So pressure comes in and plays an important role on deciding, which technology to use and which configuration to use. Next slide. Here's a cross section of the hydrocyclone liner itself. The metallurgy that's typically used in the inlet chamber is, and we've got a nomenclature there, Walnut 6. There's also Stellite 6. That's a nickel chromium boron alloy. So you can imagine the resistance, or excuse me, the erosion that could happen as you enter tangentially into that liner. So that head, I don't care whose vendor it is made of a high alloy material to handle that erosion. And then we typically make the liners out of duplex stainless steel or super duplex. I've seen them made out of Incalloy and Hastelloy with there's high H2S or CO2 in the water. So we can look at different metallurgies and we can look at different configurations of the reject flow depending on the inlet concentration. So here's a hand drawing that I did many years ago, and this just gives you a good idea of what's going on inside the cyclone. So you can see the top the top entry point is the inlet. So you've got two overflow and underflow plates that keep all that oily water inside the chamber. And what I'm doing is showing just one single liner. If you had multiple liners in there, they'd all do the same thing. But that oily water is looking for that tangential inlet. As it spins through there, as we talked before, the heavy phase goes to the outside and the oil phase goes through the middle. The number 3, where it says acceleration area, by the time the taper goes down, you're forcing that light phase to the middle of the core. And if we had a see-through model, you would actually see that oil core look like a sine wave. It's a very sine wave type configuration. But all the separation happens right after that acceleration area, and the oil actually reverses direction through the tube and goes out that what is a 1.5 millimeter reject orifice. And then the clean water or any heavies, some of the solids, will go out number 5, the clean water outlet. So in the early days, a lot of people think, okay, the oil is going out the backside. That's still got quite a bit of water with it. But from a percentage standpoint, it's about 2 to 3% of the total flow is going out the reject, and 96, 97% is going out with the clean water side. But this just gives you a good idea of, from a cross-section standpoint, what's going on inside the hydrocyclone. Next slide. And there's a picture of a couple of units that we've installed. The top left one is built for an offshore, so it's got a skid on the bottom of it. That's a 36-inch diameter cyclone. It probably handles about 100,000 barrels a day. So that's one of the things about hydrocyclones is you can get a lot of fluid through the unit in a very small, compact space. So if we think about, put our offshore hats on for a minute, that's what the real driver was to get hydrocyclones offshore, was small footprint and large throughput, depending on the pressure drop that you can get through it. And then from a maintenance standpoint, if you have to go in and maybe change the liners and inspect them, you pull off that front head and you can see the liners just are self-fitting there. And then if you need to blank off any of those spots, if the flow rate changes, you just blank them off and put it back in. Next slide. All right, let's switch to secondary. So the next slide is we'll talk about not only dissolved air flotation, but IGF. So let's look at dissolved air flotation first and describe why you'd use DAF over IGF. Next one. So some of the basic concepts of flotation, it goes back to Stokes' law, is that we're going to add now, instead of either gravity or coalescence or centrifugal force, we're going to put bubbles inside a vessel to enhance the separation. These gas bubbles are going to get introduced into the liquid, and the oil drop is what we want them to do is attach to those gas bubbles. So in the DAF, the dissolved air flotation round, we have 2 technologies. One's called Hydrofloat, and the other one's called Spid Flows, and we'll describe the differences of those. We can also, from a DAF standpoint, get more than just oil removal, because what we're gonna do, we're gonna possibly coagulate and flocculate solids out of the system before we even do any kind of deoiling. But you can see on that bottom bullet point, we can look at total suspended solids, TSS, the chemical oxygen demand, colloids, humic acids, and other organics. So there's a lot of benefits that you would use a DAF over maybe say an IGF, because an IGF is more on just typical oil removal and some solid removal, but the DAF will get many of those parameters. Next one. So here's a good picture, and this is the best way to show what the bubbles look like. I think a lot of people would think if you took a snapshot of inducing air or inducing nitrogen into a stream, you might see a lot of bubbles. It actually comes out like that picture. It's quite milky. It's a milky appearance. So the micron size of some of those bubbles can be as low as 100 micron particles. We can typically treat oil 500 to 1,000. That's kind of the sweet spot. But that picture says a lot right there, just what it looks like if you were to open the hatch and look in there. It looks very milky like that. Next slide. Few technical data points on there. The retention time in a typical DAF is 8 to 20 minutes. And a lot of times people even look at DAF compared to clarification. So there will be one slide we're going to compare what a typical clarifier would do in that GPM per square foot, as opposed to very small. So it's sometimes a better technology to pick a DAF over a clarifier, just because some of this technical data. And you'll see the removal efficiencies 80 to 98% on the solids, the COD suspended 50 to 90, and oil and grease about that same range, 80 to 95%. Next slide. So on the IdriFloat first, we'll look at why this one might be a technology of choice. We can actually add sections of this as the flow rate increases. So it's very modular. It's compact, high efficiency, and very, very small footprint for any given flow rate. Next one. So as I described, the modular unit plays an important role in being able to use the dissolved air flotation for whatever your application is. And the key thing on this slide is to look at, if you had a traditional DAF with just one chamber with several different positions inside of it, as you go through the system, the efficiency starts to drop off as the distance is traveled. But if we can look at each one of these modules, now we can capitalize on that space and minimize the efficiency drop with the distance. So you can see the next curve on the new system, it goes 1, 2, 3, 4 times, and you're just keeping your efficiency rating up high. So within Veolia, we use these in the food and beverage market and some municipal applications, and it's very efficient because of that modular design. Next one. Here's just a brief description of the flow distribution. So if you look at the circle with the cross-section drawing there, the saturated water comes in, goes into that bottom pipe, and then it's distributed to the side where we disperse the bubbles. And as those bubbles rise, it'll attach the oil and go to the top. Mixed liquid gets skimmed off the top, and your saturated water, your clean water, will go out the middle part. And one of the good parts about the water injection, yeah, thanks, Dennis, is we avoid hydraulic short circuits. So in some designs, you might get short circuiting. So this particular design eliminates that, and we reduce the chemical requirements. Next one. So now we've looked at IdriFloat. Let's look at SPID-Flow real quick. This is a high rate dissolved air flotation unit, and we use computational flow dynamics to look at where the separation would occur. Without going through all the details, we want to optimize that homogeneous blending of white and influent water. And as it goes through the SPID-Flow, you can see the blue parts of the CFD then shows how clean we can get that water. And we use the CFD to determine how to make the design. Next one. Here's a cross section of it. So typically with a DAF, we'll use chemicals to help in the aid of the separation. So the first chamber, we've got a mixer that will coagulate. The next one will flocculate, and then we have a mixing chamber in the middle, and then the separation zone goes through on the right-hand side, and then you can see on the top there's a scraper that will skim off the oil and go to the sludge, and then the water will go underneath and then out the effluent of the DAF. Next one. So here's the slide I was talking about compared to a flat bottom clarifier. So you'll see the rate is 2 meters per hour. Conventional DAF about 8, DAF plus a filter, we're talking 12, and then the spit flow 30. So that was the main driver by coming up with this design. So some of the work that we're doing onshore in the Permian Basin, we have a shale flow system, and we're capitalizing on that using this spit flow design. Next one. Okay, so now we've looked at CPIs, hydrocyclones, DAFs. Let's look at IGFs now, induced gas flotation. So as in before, we're using the similar principle, or we're utilizing the similar principle of injecting or inducing gas into the chamber so we can attach not only the oil droplets, but some of the solid particles. As I mentioned, the DAF is probably in my book better at taking out some of the solids, but we can get some flotation and effect from putting the gas into the chamber and getting some solids to remove. It depends on the weight of the solids. Bubbles size in this, typically 500, 600 micron. Inlet, the sweet spot on an IGF is in that 300 to probably 500 ppm range. So, you know, if you've got a CPI or hydrocyclone upstream of it, you can knock it down in that range, go through the IGF, and then typically get 80, 90, 95% removal, depending on the parameters. Next one. So some of the variables, the oil type, the solids type, that's one thing I didn't put a key slide in, but this is pretty much for every different technology. You look at specific gravity of the oil, you look at the temperature, you look at the viscosity, and as process engineers, we'll look at all these parameters and then determine which technology fits the best. So having a whole array of deoiling equipment helps us in that way. And you'll see on the picture that we're going from cell to cell, and as it goes through the IGF, it gets cleaner and cleaner and cleaner, and then the last section has a quiet zone. But each chamber is going to have some kind of eductor that will induce the gas and use it to float the oil out. Next slide. We've got a couple different types. This one's a mechanical. If you've been around the oil business a while, this type of flotation device has been around probably since the 40s. So, you know, a lot of different companies make a similar design like this, very, very efficient. It's a mechanical rotating piece of equipment. We'll have some maintenance, but they work really well. I know even in California, I've seen some of these older type units that are still very, very efficient with several hundred ppm, and they're getting less than 20 ppm out of it. So there's 4 active cells, just like whether it's pressurized or mechanical. And this one, by being mechanical, we're rotating that pump's rotating the rotor, and then putting all the bubbles into dispersion by that mechanical operation. Next slide. And then if it's not mechanical, we've got hydraulic. That's you know, under pressure. So this one only uses the pressure and eductors in each one of the cells to disperse the oil into the chambers. And you can see on that right-hand picture, as we were talking about that milky color, same thing. There's a picture of all that droplets being dispersed into the reservoir and letting that oil attach to it. And it can be designed for gas tight as well. Next one, sorry. A couple of applications here in Bakersfield, California. We've got a 40,000 barrel per day water treatment system with 2 of our autofloats. Influent, it's get it less than 100 ppm on both solids and oil, and 15 ppm coming out. And then I think at this application we actually have nutshell filters as well, and that gets it less than 5 ppm. So it's just an example of one of our locations. And here's the inlet and outlet configuration from a graphical standpoint. So you can see as it fluctuates, you know, between probably as low as 25 on the inlet all the way up to several hundred ppm, it stays pretty constant below that 25 ppm range. You'll see little spikes as the oil concentration goes up, but it stays fairly constant between 10 and 25 ppm. So it's a very good example of how efficient they are. Next one. Here's one in Bahrain in the Middle East. We got 55,000 barrel a day, 3 Model 55s. Influence a little more on this one, 300 and 120 on TSS. Effluent less than 5 and 20 on the solids. So the on-site performance is about 85, 90% removal. So that's another just case study we have. Next one. And then even in the SAGD market up in Alberta, up in the cold country, a lot of them use a pressurized design, and you can see they're insulated to handle that cold temperature. This one's actually at Suncor Firebag, way up near Fort McMurray. Next one. And then on the downstream side, I know we've talked a lot about oil and gas on the upstream, but a lot of these technologies are used in the downstream market. So this is a case at an ethane cracker process. Same thing, it's removing oil from water as well as solids. And this one also has a nutshell filter downstream of it. So if anybody's interested in looking at IGFs or nutshell filter for downstream applications, we have them in there, and they're doing a very good job of removing oil and solids. Next one. All right, the final one is tertiary, and there's several technologies that we can use in tertiary, but for time constraints, we're just going to look at the nutshells. So back in the probably late 70s, early 80s, there were several companies that looked at alternative media to replace sand filters as a tertiary means of oily water separation. So they looked at coconut shells, they looked at walnuts, they looked at quite a few different shell media, and the nutshell, the walnut shells, rose to the top and became a very, very efficient medium to separate oil and water at the very low levels. Next slide. So oil droplets act just like solid particles. So in this tertiary phase, we're probably less than 50 ppm in most cases. Matter of fact, we like it to be less than 50. So we can operate the media bed and only have to backwash it once a day. So the reason that the walnut shell filters rose to the top is because their modulus of elasticity is very, very high. So they don't break down, kind of like even anthracite or garnet. So back in the day when they would use sand, after a while it gets spent, you'd have to just destroy it. It was not good anymore. You have to keep adding and adding sand. So when walnuts came around, they were very efficient at reducing the oil and solids. You get some solids trapped in there. It's a secondary benefit, but mainly it's a nice polishing filter in that tertiary mode. Next one. So 98% removal. So see, we can get a higher efficiency with the walnut shells in this range and get the suspended solids and insoluble hydrocarbons down at about the 2 to 5 micron range. The flux rate we use is in that range, 8 to 12. Sometimes we can push it a little higher, and sometimes we push it a little lower, depending on the constraints. And then we backwash it. So go to the next slide. Actually, there's one more, but let me just talk about this first. Yeah, so when we backwash it, the media is actually going to come out of the vessel to scrub off any hydrocarbons or solids that are on it. So on that picture, you'll see there's a pipe there that's got a scrubber inside of it, and it's not actually scrubbing the oil. The pump actually breaks the oil and solids off of the media. This keeps the media from escaping out of the backwash. So you can see there's at the top, there's an inlet part where it goes through the scrubber, and then there's another port that goes back into the vessel. So we're taking the media out and through different sequences, cleaning the media or cleaning the oil off the media. Next slide. There's a good picture of it. So the walnuts are actually crushed. They're not just big chunks of walnuts. So there's, a couple of different manufacturers that make it, and they're black walnuts. They have to be black walnuts. Um, and, that media sits in the bed. It's about 66 inches of bed depth inside the vessel. And then on the top picture, you see the gentleman there pulling out the scrubber. So if it needs to be cleaned, it's easily accessible either the top or on the bottom. Next one. And then this is our final slide. So this, we just wanted to show the sequence. So when the media is sitting there, we're filtering through the vessel, and then we fluidize it. After fluidizing, we discharge the waste. And as I mentioned, the media actually comes out. We go through the scrubber, we clean it, and then it goes back into a settling mode. We purge the air out of it, and away you go back through filtration. So from a final step, onshore applications, this is probably the most used technology that I know of, even our company knows of. We tried different medias, but walnut shells are still, I call it the king of the tertiary range as far as effectiveness and how well it can get the effluent. So typically, if you need oil down to less than 2 or 3 ppm and the solids in that same range, this was a great final step in any kind of oil and water separation. And I think that's it. I'm just about almost out of time. So if anybody has any questions, just send them on there and I'll be glad to answer them.
If anyone has any questions, we actually don't have any right now. If anyone has any questions, feel free to type it in. I'll give you 45 seconds if anyone wants to type in a question. We have several comments in here, but no questions. Here's one. Will these slides be available after the webinar? Yes. On Monday, everyone will have in their inbox this entire presentation recorded. So all you have to do is click on that, and you will have the entire presentation. We have a question. Do you have an office in Calgary, in Alberta? And the answer is yes, we do.
Yes, yep.
Do you have any more comment on that? Here's another question. Which is the minimum API that could handle the hydrocyclone?
Oh, good question. So when you say minimum, I guess it can handle the range of from about 12 to 13 API all the way up to about 55 API. So I have done tests on it in heavy oil. It's tougher to get that because in Stokes' law equation, that specific gravity is closer to water. I would say from a general standpoint, if it's less than 20 API, it'd be a tough fit. I would recommend pilot testing it. But I have done some tests where I've separated oil and water and a pretty steady stream at 13 API. So I've done them in Venezuela, I've done them in Bakersfield where it's very heavy oil. But you don't see too many hydrocyclones at that low level.
I'm sorry, what drives the decision when choosing between a spid flow or EdraFloat?
That's a good question. The EdraFloat is, like I said, it's more used for light industrial applications. So since we've been talking mainly about oil and gas, we tend to go to the spid flow design because it's more robust. It's the metallurgy. A lot of time it goes into metallurgy. So we didn't talk too much about metallurgy between the two, but the spid flow is designed for higher TDS water with the chlorides. So I would tend to go spid flow for oil and gas applications and the EdraFloat for light industrial.
Okay. Here's one that just came in here. Are there general cost guidelines for the different technologies?
Yes, and a lot of times what we'll do is give you an idea of what a cost per barrel range. So, if you look at hydrocyclones compared to IGF and they both fit the window, then we would just tell you what a cost per barrel will be. You just give us the flow rate, and then we'll say based on your parameters, this might cost you $10 a barrel to treat, or it might cost you $20 a barrel to treat. So that way you can get a rough idea from a commercial standpoint or cost standpoint which one to pick, if they both fit technically.
Okay. Here's another question here. What are used for coagulants and flocculants?
Different polymers. I'm not a chemist or a chemical engineer, so I'll have to table that one. I can find out for you. So if you want to leave us your name and number, and we can get back to you. But I'm not exactly sure. But I know they're different polymers, and it's then we pick the chemistry based on the inlet concentrations.
Okay. Dwayne, here's another question. Those hydrocyclones for offshore applications could be used for onshore? And that's a question.
Yes. So I've got an application right now. I've got a customer that they drill brine wells. They don't actually drill oil wells, but they're after the salts. So they want to make bromine and bromide. So it's an onshore well, and they are using a hydrocyclone because of the costs and the small footprint to spin out a little bit of trace oil that's left in some of those wells that are mostly water. So, they can use them, and it's used onshore, and it does. The drivers are both efficiency of the cyclone for the specific gravity of oil that they're trying to remove and the footprint. So even though most land operations are not real estate constrained, some of them are, and they're trying to fit something small into that spot. So they picked an onshore application. One more comment too, I actually did a test onshore in the Permian Basin off of a wellhead and took 2% oil down to less than 100 ppm, and it was an onshore application. They wound up buying one and putting it on location, and it reduced the amount of oil that they sent to their water treatment facility. So yeah, there's quite a few applications for using them onshore, and Canada. I've done several of them in Canada as well.
Okay. Okay, so that's all the questions we have. I just wanted to remind everyone that the next webinar for oil and gas companies is on November 7th, and it will focus on high recovery membrane technologies. And you can get on veoliawatertech.com /events and sign up for that today. And just a reminder to everyone that as soon as I finish this webinar, a 3-question survey will pop up. It'll just take you a moment. If you would fill that out, that would be great. Thank you to everyone for attending today. Thank you to Dwayne for presenting. Everyone have a great day.
Thank you, guys. Thank you.